So this talk is about the lemma, which has, I guess, various names. Some people call it the Sauer lemma. I know it as the Sauer-Shelah lemma, and people in Israel sometimes call it the Sauer-Shelah-Perles lemma. Okay, so only two of these people actually published the lemma. And I think some of them, if you look at the paper where the lemma is supposed to be stated, you won't really find it. Okay, but that's a very classical result, I guess, in model theory or statistical learning theory or combinatorics, whatever you want to call it. So this is joint work with a bunch of people, only some of which I've actually met in person. So I might be mispronouncing their names: Stijn, Cambie, Bogdan, Chornomaz, Zeev, Dvir, and Shay, Moran. Okay, and they're spread out around the world. Okay, so what is VC dimension? So this is, okay, VC stands for Vapnik Chervonenkis, two pioneers of statistical learning theory. And this is a kind of a parameter of a family of subsets of a set X. Okay, so here you have an example. So this family is called F and consists of binary vectors, which we identify with sets of the elements X. Okay, and what's the VC dimension of a family? Is the maximal size of a shattered set. Okay, and what is a shattered set? So here's an example. So it's a set of elements, a subset of X, where if you go across the family F, then you see all possible patterns. Okay, so if your set is of size D, then you need to see all 2 to the D possible patterns. Okay, so this is the VC dimension of a family of sets. It's the maximal size of a set which is shattered. So in this case, the VC dimension is 2. Yeah, so no set of size 3 is shattered because in order to shatter a set of size 3, you need to have in particular at least 8 elements. Okay, so this is an example of a family with VC dimension 2. Now, why do we care about VC dimension? Okay, so VC dimension shows up in several places. My excuse is learning, although I don't know much about learning. So you can see here the connection. The hypothesis class is pack learnable, whatever that means, if and only if it has finite VC dimension. Okay, so I'm not going to explain anything more, but just the way you should think about it is, if you care about statistical learning theory, then really the most basic concept is VC dimension. Okay, so the reason somebody like Shelah was interested in is because it comes up in model theory. And it's also a very natural combinatorics parameter. Okay, so now that we've explained what's the VC dimension, then I can state the Sauer-Shelah-Perles lemma. And it answers the following question. So suppose I have a family and its VC dimension is D. How big can it be? Okay, so here's the answer. So suppose that my underlying set has size n, then a family of VC dimension D has at most n choose at most D elements. Okay, so this n choose at most D is just n choose 0 plus n choose 1 plus n choose 2 plus n choose D. Okay, this is not sure how standard this notation is, but it's quite self-explanatory. And this is started because if you take the collection of all sets of size at most D, then you can convince yourself that it has VC dimension D, and it contains exactly n choose at most D elements. Okay, so this is the Sauer-Shelah-Perles lemma. We'll discuss how this kind of thing is proved soon. But first, a corollary, so a dichotomy theorem. And this is about families of subsets of an infinite set X. Okay, so here's the deal. So we look at the projection of our family onto some finite set S. Okay, so we just, S is a subset of X, and we intersect all sets in F with this set S, and we see what we get. So there are basically two options. If the VC dimension is finite, then this thing grows polynomially with the size of S. In contrast, if this set is infinite, then what this means is that for every D, we can find a set S of size D, where this projection has exponential size in D, 2 to the D. Okay, and this is one of the reasons why VC dimension is important, I guess. Okay, so this is sort of all I want to, most what I want to tell you about VC dimension in the classical sense. And now more to the point of this talk. So we're going to talk about generalizations of VC dimension. And like maybe the most obvious generalization is a Q analog, okay? So people in combinatorics, for some reason, they really like Q analogs, okay? So they see some concept for sets and they say to themselves, like they ask themselves, what happens if instead of sets, I look at subspaces? Yeah, so can we define the VC dimension instead of for families of sets, for families of subspaces? Okay, so we fix some finite field and now we have a family of subspaces of some n-dimensional finite field, and can we define a VC dimension for subspaces? Okay, so in order to get some idea of how we might do it, here's a different way of defining the VC dimension for sets. So recall that the VC dimension of a collection of subsets of X is the maximum size of a shattered set, and one is a set shattered. Okay, so a family F shatters the set S. If when we intersect the sets in a family with S, then we see all the subsets of S. Okay, so here's the example we had before. And I'm claiming that the set 2, 3 is shattered. And why is that? Because if I intersect 2, 3 with all the families in my set, then I get to see all the subsets of 2, 3. Okay, so this is we haven't done anything, and you'll see in a moment why it's important to switch from 0, 1 vectors to this point of view of sets. Okay, so here's the definition we had before. And now it's kind of obvious how to generalize it to vector spaces. Okay, so we're going to replace size by dimension, and we're going to, well, replace intersection by intersection. Okay, so now we have a collection of subspaces of f to the n. And its VC dimension is going to be the maximum dimension of a shattered subspace. And when is a subspace S shattered? If when we intersect the subsets in the family with S, then we get to see all of the subspaces in S. Okay, so this is sort of the first thing you would think of, and it's a definition that makes sense. And how do we know that it makes sense? Because we can generalize the Sauer-Shelah-Perles lemma to this setting. Okay, so we get exactly the same statement, only instead of n choose at most d, then we have the Q analog, the number of subspaces of f to the n of dimension at most d. Okay, so we proved this sort of independently, but then there's this unpublished manuscript of Bogdan and Funkel, which is called something like the linear algebra method in combinatorics, that I actually got to see physically during my PhD studies. So while our proof is a bit different, it cannot be ruled out that I glanced at the proof back in my PhD and just forgot about it. So it's possible. Okay, but definitely Bogdan and Funkel, they proved it before us. Okay, so now let's talk a bit about how this kind of thing is proved. But first, any questions about the definition or the statement? So I'll take this as a no. Okay, so here's the original Sauer-Shelah-Perles lemma. And we're actually going to prove something a bit stronger. So I'm not sure how to pronounce this guy's name. So I'll say pager, but it's probably wrong. So instead of saying that if a set has, if a family has a VC dimension D, then it contains at most size of X choose at most D sets. Let's say that every family shares at least as many sets as its size. Okay, and why does this imply the Sauer-Shelah-Perles lemma? So suppose that a family has size more than X choose at most D. Okay, then it shatters at least, suppose the family has size more than X choose at most D. Then it shatters at least X choose at most D, or rather more than X choose at most D sets. And in particular, it has to shatter some set of size D plus 1. Okay, because there are only so many sets of size at most D. And hence, its VC dimension is at least D plus 1. Okay, so I'm not sure if you followed, but this is kind of very simple. So we're actually proving this strengthening because all known proofs of this the Sauer-Shelah-Perles lemma, they actually generalize to prove this strengthening. Okay, so here are three different proof ideas. So one proof is using induction. So we decompose the family into the parts containing some element X and the parts not containing the element X. Okay, this is pretty straightforward. It just works. Another proof is monotonization or shifting. So if your family F is downward closed, then this SSP lemma, or rather its strengthening, is obvious because your family shatters exactly the sets in the family. And then you do some sort of downshifting, and you see that you show that this only increases the number of sets which are shattered. Okay, so this is also a nice exercise. But somehow, if you want to generalize these two methods to vector spaces, they don't really seem to work. So for method number one, we can try to do it because we can define X in S and X not in S. But somehow this X not in S case is not as nice. It just doesn't seem to work out. For the second method, then this is like doing shifting for vector spaces, which people have tried to do, but yeah, we don't really know how to do it. Okay, so these two methods don't seem to generalize to vector spaces. But there is a method which works, and this is the so-called polynomial method or linear algebra method. And this is a very weird method. Okay, so that's what I'm going to explain next. Okay, so this is what we want to prove, and here's the idea of the proof. So we're going to look at the space of all functions from our family to the real numbers. The real numbers, you can replace it by anything else. And we're going to show that every such function can be expressed as a linear combination of monomials which correspond to shattered sets. So why do I mean by a monomial corresponding to a shattered set? So suppose that my family shatters the set 1, 2. So the corresponding monomial will be x1, x2, where I think of the inputs like x1 is equal to 1 if the input set contains the element 1. Okay, so basically the monomial corresponding to a set S, it means that the input contains the set S. Okay, so this is the idea, and now we compare dimensions and we get this strengthened form. So we know that we can represent every function as a linear combination of some monomials, monomials of arbitrary sets. So what we need to do is we need to get rid of the sets which are not shattered. Okay, and so how are we going to do it? So we're going to show that if our family doesn't shatter some set S, then the corresponding monomial, we can express it as a linear combination of smaller monomials. Okay, so this expression won't work for arbitrary sets, but it will work for functions whose domain is F. Okay, and now I'll show an example, and hopefully all of this will be crystal clear. Okay, so let's say that my family doesn't shatter the set 1, 2. And why doesn't it shatter the set 1, 2? Because, well, no set in my family contains both 1 and 2. Okay, so this is one reason for it not to shatter the set 1, 2. In that case, this monomial x1, x2 that corresponds to the set 1, 2, it just equals to 0 because no set in the family contains both 1 and 2. Okay, so now suppose that the reason for which this family doesn't shatter 1, 2 is because the intersection of no set in my family with 1, 2 is equal to exactly 1. Okay, so in this case, I know that if my set contains 1, it also contains 2. Okay, so I can replace x1, x2 by x1. And the most complicated case is if no set in my family is disjoint from 1, 2, and then we have this formula here that you can check. Okay, so I can express x1, x2 as x1 plus x2 minus 1. Okay, so I'm not sure if you could actually follow. It's not too important. The point is that whatever this proof is doing, we can extend it in a very straightforward way to vector spaces. Yeah, so this thing just works more generally without doing anything special. Okay, so this was this linear algebra proof, which is a kind of magic. It's not so clear why it works, and we'll see in a moment that not only is it not so clear why it works, it's also, it breaks up in some cases, and it's not so clear why. So we'll see in a bit. Okay, so actually, so now we have VC dimension for families of sets and VC dimension for families of vector spaces, but we could ask what happens in an arbitrary lattice. Okay, so in order to talk about VC dimension, so well, basically, in order to talk about when some element is shattered, we only need to have a meet operation. So it's enough to look at a lattice, and if we want to define a VC dimension, we need the lattice to be graded. Okay, so I'm not going to discuss lattices too much. I just say that this kind of proof, it works for any geometric lattice, which is a lattice of flats in a matroid. And here are some examples. So if you start with the uniform matroid, then you get the usual Sauer-Shelah-Perles lemma. If you start with the linear matroid, then you get the Q analog. And if you take a graphical matroid, then you get some sort of result for partitions, which is a bit awkward. Okay, but this thing actually doesn't work for every lattice, and we'll see an example in a minute. So what is the condition which is needed for this argument to work? So we need the Möbius function of the lattice to never be 0. Okay, so the Möbius function is sort of the coefficients of the inclusion-exclusion formula for the lattice. And why does it show up? So it shows up because in these identities, then, well, all these coefficients are really values of the Möbius function. And what we need is that for the value of the Möbius function on the left, like corresponding to x1, x2, this thing should be always non-zero, because otherwise this proof doesn't work. So this is why we need the Möbius function to never vanish. And there's a result saying that in a geometric lattice, then the Möbius function never vanishes, because up to sign, it counts something which is always positive. Okay, I forgot the name of the result, but this is something very classical. Okay. Questions up to now? Okay, so let's continue. And now what's going to interest us is when does the Sauer-Shelah-Perles lemma hold? For which lattices? Okay. So for which lattices does the following thing hold? So this is really this strengthening due to pager. If we have a family, or rather every family in the lattice, it shares at least as many sets as the size of the family. Sorry, at least many elements as the size of the family. Okay. So what this Baba-Frankel argument, which we also repeat in a slightly different way, shows is that if the Möbius function of the lattice never vanishes, then this result holds. Okay, and here's an example where the result doesn't hold. Okay, so here the lattice is the number 0, 1, 2, where 0 is the smaller than 1, smaller than 2. And I'm taking the family 1, 2. And the claim is that this family only shatters the element 0. Okay, so this is kind of, you need to verify it. It's not too complicated, but you can check. So in order to check it, we need to take the meet of our family with all the possible elements with 0, 1, and 2. And when we do this, we see that only 0 is shattered. Okay, so yeah, it's all on the screen. And indeed, the Möbius function of this lattice vanishes between 0 and 2. Okay, so this does not contradict the Baba-Frankel result, and we have not found a contradiction in mathematics. Okay, so now you might conjecture that the SSP lemma holds for a lattice if and only if the Möbius function never vanishes. Okay, so this is a reasonable conjecture, but unfortunately it's false. So here's an example of a lattice for which this lemma does hold, but the Möbius function does vanish. So in this case, the vanishing Möbius function is between 0 and 1, 2, 3, 4. You can check. And here's this example again, where the SSP lemma does not hold this 3-element interval. And we can generalize this example. So if my lattice contains an induced 3-element interval, so this means points x, and z, where there's only exactly one point y between them, then also a similar kind of example shows that the lemma fails. Okay, so now I can state our main conjecture. Yeah, and this conjecture says that this SSP lemma holds for a lattice if and only if it doesn't contain an induced 3-element interval. Okay, so this kind of 3-element interval is the only obstruction for the SSP lemma. Now, why is this interesting? Because this condition of not containing an induced 3-element interval is actually found in the literature. Yeah, and it goes under the name relatively complemented. Okay, so when is a lattice relatively complemented? So a complement of an element y is an element y prime, such that the meet is like the bottom element of the lattice, and the join is the top element of the lattice. And the lattice is relatively complemented if every element has a complement relative to every interval. Okay, which is what's written on the screen. And you can easily see that, well, this 3-element interval is not relatively complemented because 1 doesn't have a complement with respect to the interval 0, 2. Yeah, so this explains the name relatively complemented. And Biona showed that a lattice is relatively complemented if and only if it does not contain a 3-element interval. And we can conjecture that the same condition is also equivalent to the strengthening of the Sauer-Shelah-Perles lemma to hold for the lattice. Or maybe, it's a conjecture, but I think some of us actually are not so sure about the veracity of this conjecture any longer. Okay, so we have some partial results. Okay, so here's again this result of Baba and Frankel that we reproved. So we can show that if the lattice is relatively complemented, that the Möbius function does vanish, but only for the minimal and maximal element. Then the SSP lemma holds. Okay, so this is one thing we show. We can show that this SSP condition is closed under taking products. So this is just the usual notion of product of posets. And we also have like a more complicated condition, which shows that something like SSP holds for some families when the lattice is relatively complemented. But basically, we have no clue if our conjecture is correct. So I think right now, Bogdan, who's now one of the co-authors, has been trying to construct a counterexample for some time now. And I think that so far he hasn't succeeded, but sort of he's not so sure any longer that it's impossible. Okay, so maybe the conjecture is false. And in that case, instead of asking us to prove the conjecture, we will ask what's the correct condition that is equivalent to SSP holding. Is there a reasonable condition which is equivalent to this SSP condition for a lattice? Okay, so that's all I have to say.